Hello and welcome back to the Hyperthesis episode 100, the very special episode because we have for the first time our face reveal. Well, apart from the Instagram, but welcome. My name is Feely.
I'm Patrick.
And I'm Liam.
All right, so we are back for probably one of the last episode for a while. So we're gonna go on an extended break after this, to reorganize ourselves, and also we are near our end of our degrees. So we're gonna try to finish that up, and perhaps when we come back, we will have some title on it, on us. Well, anyways, let's get started. Liam, would you like to get us going?
Yeah, so I didn't prepare an intro topic, but I was at a conference in Europe that I can talk about. Just kind of wing it. So a few weeks ago, I was in Nottingham for a conference on analog gravity. It was called the Quantum Simulators of Fundamental Physics Community Workshop. So not everyone in the analog gravity field was there. So I guess for some background, we've talked about analog gravity before. Well, I have at least many times. But it's this field where you make things in a lab that mimic things in outer space. That where quantum gravity is important. So quantum gravity is this regime where quantum mechanics and general relativity are important. And it's a theory we haven't figured out yet. So it's very complicated. No one has developed a full theory of quantum gravity, but we've got workarounds. And one of the big problems in that field is experimentally testing things is really hard. So, in the Big Bang, we think that something like the Big Bang happened, but we can't really reverse time to go check. And we can't really get near black holes to see what happens, or we can't see Hawking radiation from them. So we don't really have any way to properly test quantum gravity right now. And that's a big field. Lots of people work on that. But these tabletop experiments, they're not quantum gravity, but you can make them mathematically equivalent to what you think quantum gravity might be or what quantum gravity is. And that's like the point of the conference is people who study this.
Well, I got to point out, we have a guest today. In your background is Rusty, just hanging out.
We can see him in our videos, but I don't think my phone video can see him. And I'm afraid to move my phone because I hope I have it centered on my head right now.
No, it's okay.
I'll send you a photo of my cat or something.
No, we will do the inset. It's like, that's the cat.
Yeah. Okay.
That being said, and talking about special guests, were there any kind of special people that you were able to talk to or meet with or play games with during the conference?
Well, yes, indeed. So, yeah, so at this conference, it was a really cool conference because it was kind of this so analog gravity is a very weird field because you're combining gravity, you're combining quantum mechanics, you're combining these ultra cold gases and optics and solid state physics. You're combining a lot of different things into one field. Even classical mechanics, like classical wave mechanics, like ocean waves and stuff like that. That's also a big field. So it's kind of this, you kind of have to know a lot about everything, and you have to be able to talk about all these different things to people when you communicate your work. So when you write a grant, you have to be able to somehow summarize like 6 to 8 different branches of physics in a single thing. And yeah, so a lot of these analog gravity people, they really work hard on community outreach. So doing like public things for people who aren't scientists or people who are scientists in different fields. And so they had like they work together. This group at Nottingham, they're led by the physicist Dr. Silke Weinfertner, she was actually one of Bill Unruh's postdocs or something. So Bill Unruh is this very famous physicist from Canada who's known for this thing called the Unruh effect, but he also created analog gravity, which we've talked about before. He wasn't at this conference, unfortunately, but I've met him before at a different conference. But so Silke Weinfertner, her group was hosting this, and they get a good amount of money for what they do because they do really good experiments. They actually made the world's largest quantized vortex. So they made a big superfluid helium vortex made out of quantized particles with quantized units of angular momentum. It's massive and it's really cool to see. And they made this big water tank experiment. They do all this other crazy fun stuff. But they commissioned artists, so they paid like 5 to 8 artists to create like art exhibits with like physics motivation in mind. And so part of the conference was we got to go see these art exhibits, and they also created a Lego interferometer design, and they put together maybe like 100 of them. Maybe I've got the numbers wrong, but they're going to send them out to all the high schools in the UK and teach the physics teachers how to teach their kids about not matter wave, but just regular optical interferometry. They also had an entire day, because analog gravity is really weirdly debated topic, because it's like just because you see something in an analog system doesn't mean it really tells you about real quantum gravity. So a lot of philosophers in physics have gotten very interested in analog gravity. So there was like a whole session devoted, all these like physicists turned philosophers came and like talked about it and stuff, which was interesting. I thought it was pretty cool. There was some, I don't know, when you get into philosophy, things get tricky because it's not quite science and it's not quite it's not quite math. So not the things I'm used to. But yeah, so there's a lot, and I'll show you some pictures. All right, so I'm going to share my screen, and these will somehow appear in the video, hopefully, or something will. Share screen. So here's the web page for the workshop, and we don't necessarily need to show this. But for the events, so they hired these artists. They actually paid them with grant money to like create a VR experience where you could go and experience quantum tunneling. I'll show you some photos, but they made this Lego interferometer, and we got it to work. We got the tour of their laboratory, which is good. They had the Michael Berry, so this other famous physicist I've talked about before, who was my supervisor, came and gave a talk. So I got to meet him again and actually talk to him a bit.
Sir Michael Berry.
Yes, Sir Michael Berry. He was knighted because apparently he's done really good things for physics. We got to go see, they had these really cool art displays. I'll try and find some photos and send them to you or something, but they're pretty cool. They had this giant one called Ring Down, which was like inspired by when two black holes orbit and they merge and you get that LIGO signal that we learned about during our undergrad. So they had a whole thing, and the thing moved. They press a button and they spin and they make noise and they connect to magnets on the outer edge of this cage. You can see them moving, so it was quite cool. And I have some photos here to share with you. Open them. I go between them. So
I like the timing of the photograph because you were the only one that closed your eyes.
Yeah, I know.
Is it in all the photos?
Not all the photos. Actually, Duncan, my supervisor, does it in a photo. So here's a photo of me giving my talk. And actually, this is a room Einstein's given a talk in, or a few talks in. There's like a plaque right next to me you can't see, just off screen, where it's like, Einstein came here on this date and gave a talk. Because that's something that you see a lot in the UK. You go places and they have all these plaques everywhere, and they're like, this is where Sir Isaac Newton took a nap on this day at this time, and a squirrel sat on him. Like, there's really weird plaques everywhere because, things are so old. Like, you go to these universities and they were founded, or I went to a bar called Ye Old Trip to Jerusalem. The bar opened in like 1162 or something. It's like older than Canada, wow, right? By like a long shot. So you get a lot of stuff like that. So there's like commemorative plaques everywhere. They've just built up over the years. So this was really cool to give a talk in a room. Einstein gave one in.
I want to go to the place where Tycho Brahe lost a duel and lost part of his nose. That'd be hilarious. Like, oh yeah, this is the place the famous astronomer lost his nose. And
then what they didn't have question sessions after every talk, but after every like 4 or 5 talks, they got everyone up on the stage and they did like a 30-40 minute panel with the whole, because there's only like 100 people there. It's a fairly small community, which is really cool. So I got to be on a panel, and yeah, I was kind of looking at my toes there for whatever reason. But Michael Berry asked me some good questions, and some people asked me some other questions. we'll get to this one in a second. This is the whole group. So this was one of the this was a different room we did the presentations in, but this was the whole group. There I am in the back here. Duncan's in there somewhere. I see Michael here. But it's a really good group of people. Decent amount of Canadians. There's me giving the talk again. The photos didn't go in the order I wanted them to. There's me in the back staring at the camera for some reason. I caught them. Another panel photo. I don't look too impressed, but I had a blast. And then they had a reception where there's this church that they turned into a giant bar, basically. They rented out the whole first floor of it. So me and Michael, Barry, and Duncan are here drinking some gin, because of course we are when we're in England. I actually
You got some drip too. I like it. You know, you look like
I'm wearing the same shirt right now. Actually, I don't
look like the cool guy.
I don't have the suit on or anything, but I walked up to Duncan and Michael, who were talking, and Michael Barry looks at me and he's like, "What's that?" And I'm like, "Gin and tonic." And he's like, "You get that over there?" And he like points at the bar, and I'm like, "Yep." And he's like, "Brilliant," and just starts walking over. So that was kind of funny. And then that's a big glass of gin. Okay, I wanted to include more photos, and I guess I forgot to, but they had a day when they did the lab tours where they gave us all these Lego interferometers that they were gonna send out to the high school students, and they're like, "All right, everybody build these, and if you want." So we built it, and I have some more photos. They're not here, unfortunately, but we got the nice interference pattern. It was really cool. But it took like Michael Barry, one of the most established physicists of all time, and like 5 to 6 other well-established physicists, plus maybe me and a couple others who weren't, to like make one of these in an hour and a half. And you can notice that there's some wine in there, and I think that had something to do with it. Took us a while to get it sorted, and we're all theorists at this table, so like that didn't help.
I was going to say, when a theorist tries to do something lab related, it tends not to go well. So they may be well-established physicists, but only in theory.
Theoretically. I have a
theoretically well-established.
I'll theoretically have a degree in physics.
Hey, maybe the wine was the helper because it's a performance enhancer, right? Maybe without the wine, it would take longer.
Yeah, but part of it was that I forgot my undergraduate optics, and I was like, "Is this the interference pattern?" And it was just like the airy fringes that you get from thin lens interference, because there's like a lens you have to put it through. Like, I don't know, that's not the interference pattern, is it? And then we eventually figured out that we hadn't aligned it right, so we aligned the laser from the mirrors, and then you get this really cool, like, diagonally moving oscillation pattern. So yeah, I gave a talk. It was really cool. It was a really good conference for my career. I have all these projects now that I'm doing and working on. I've got all this nice code that I'm working with people in Heidelberg on this stuff now, and I had an experimentalist working. I don't want to say they're working for me, but they're doing experiments on my theory. It's great now. It was a really good week for me, so I'm quite excited about it.
Yeah, I'm glad that, because sometimes it's hard to be in the last year and then be busy with trying to finish and try to publish out a paper, and then you got to think about the future, and a lot of times it comes down to who you know, right? Because how do you prove your merit? By showing your work to people and then talk to people so they know. So it's like much better than a dry application. That's like, well, who is this guy that's coming in, and there's no one that they know. So I think this is a great social event, and I'm pretty sure that you get to experience the beautiful campus and beautiful university historical place.
It was such a well put together conference with all this extra stuff too. Like even ignoring like the art and all the other things, it was really good. And then you put that on top of it, and it was like, oh, that was awesome. So shout out to Dr. Weinfertner's group at Nottingham and anyone else who helped with it, because I find this analog gravity community pretty collaborative. Everybody no one's really out to get each other, I have some stories about that, actually, which is a recent development with another group who may or may not have stole one of my ideas, but that's a whole other topic I don't want to get into. I don't know if they did, but there's like good evidence that they might have. I don't want to say stole, but They pulled a dirty one on me. So, but it wasn't from an analog gravity group, so that's fine by me.
I do just want to say about your conference, I really like the idea that they just kind of put the speakers in a panel
Yeah,
afterwards and have them answer questions, because there's always a lot of pressure on speakers to answer questions as best as they can in like 2 or 3 minutes between talks. And I like the idea of being able to form a panel and then just kind of, once you have more time to think about things, especially you said it was like an hour or something after the talks. And then also you can like feed off of other presenters who are interested in the same thing. Like that's such a cool idea, and I think needs to be more
yeah.
present in
It was the panel
conferences.
was directly after the talk. So if you gave the last talk, your panel was just like immediately after. But it was nice because, like, I don't know, when I was on stage, I was getting asked really hard questions, and I didn't feel any pressure because it felt like a group discussion more than it did just being like, tested by people in the audience. It felt like the whole audience and the panel were talking back and forth, like trying to figure things out together. So it was quite cool. I didn't feel like stressed at all, even though people were asking things I had no clue about. Uh,
Yeah, that's
yeah,
the one thing, right? That a good work environment, a good collaborative environment does, where it allows people to feel less pressure when they ask questions, or don't feel that is they're out there to challenge your intellect or challenge your project, but it's more like curiosity to learn more about your project, because
yeah,
perhaps they have similar experience where they try to explain these things that sometimes the ideas are very unconventional. You're trying to explain some new things, and a lot of time people are skeptical about it. And it's like a skill to learn how to ask questions, being like without being like derisive or all these make people uncomfortable and try to like it's a thing that I think I learned slowly on it. Like, well, how do you ask questions by not challenging their like personal self, but more like, we are just curious about your project. Could you tell me more about it?
yeah. Because at like the end of the day, it's your job to ask questions that are difficult and scrutinize things. Make sure that they're doing good science and not just bad science, or that they're just hooked on an idea and they're biased towards it because they've researched that for 40 years or something, right? So it's kind of your job to pick what they've set apart, but you're also, at the end of the day, we're all scientists and just trying to learn things. So it's like people have their own agendas, but it's kind of weird to me in that sense, because it's like you're just trying to figure out the truth, I guess. um maybe one theory doesn't agree with another, but they both give you the same thing. So it's like they're just different ways of thinking, and everyone's just trying to figure out what's what. So it makes sense to me that like people work together, and you're not trying to like attack someone when you're just asking them about things, or trying to, I don't want to say pick apart, but like make sure that whatever they've done is legit.
Yeah, but I can see how some fields are much more adversarial or vitriolic, right? Is when it comes to, let's say, funding, when money got involved, I think it can get really nasty. But I mean, the I think analog gravity is something so niche that everybody feels like, hey, I just want to know how other people model gravity and how are they going to show these effects, right? So these are really cool. Where I think I don't know which field are super competitive, but I'm guessing the ones with a lot of industry applications or all these like grant
Met
money that are very competitive.
Medical physics, probably, like just anything where you get money involved, it starts to become quite competitive. And anything that you can, like, patent things or create stuff to sell, you got to be a bit more secretive, because it's ruthless out there. Like, if someone steals one of my ideas, it's like, well, it's not really the end of the world. I'm not losing out on potentials for millions of dollars. um which it still sucks, but it's a bit different, I think, for me at least. Maybe I should be more careful about what I say. But
No, I've definitely heard that about medical, like just medicine research in general, where I've had friends who have done, especially like cancer research or kind of disease research, and they said that they have to keep lab books. Nothing can go online or on a computer. Everything has to be written in a lab book about like their experiments, their tests, and everything. It has to be in pen, and those lab books are stored in a safe.
Wow.
And it's just there are so many levels of security with medicine because you want to be the first lab to be able to like find the drug that cures a certain type of cancer, or like find out exactly what causes Alzheimer's or things like that. And so there's there's some very intriguing stories of kind of deceit and stealing and all that within the medical field. So it's refreshing to hear about like the camaraderie and in your conference and kind of these smaller conferences, and I wouldn't say less competitive fields because everyone's trying to kind of get ahead and do the best that they can, but
Yeah.
certainly a lot more chill than having, say, your laptop locked in a safe every time you're done
Yeah, I'm
using it.
sure there is some like stuff that happens like that. I think it happens everywhere, but it's definitely way more relaxed. Um, like I'm talking about things with people that aren't published, so it's like that's already completely different than some more money based fields would do. They would only talk about published things.
See, I think my lab is in, well, the Sterling Hall at Queens. I think we have security through obscurity because you get lost all the time. If you are new you come here to give a talk, we basically have to have a guide sometimes. If you're going to go to the basement, it's like a maze. So it's kind of funny. It's like, well, you want to come steal our work? Good luck at finding the room.
So I thought it was kind of like fun to talk about that analog gravity stuff today, because I think the first episode we did, we talked about. Well, I talked about my research, and that was like 2000 or that was 2022, I think. So I probably explained it quite poorly, but kind of 100 episodes later, we made it pretty far. It's been what,
Yeah.
like 3 years of this podcast, which is crazy to think about.
Yeah, it's like a Ouroboros, right? The snake that eats his own tail. It's this come back to the beginning, but not everything is about you, Liam. Not everything about analog gravity. But
What do you
I think
mean?
it's nice to hear this. Like, do you find your understanding of gravity or understanding of your project when you start and now, like, is that a big difference?
Yeah, you completely different. Even between now and the last few weeks, like I just feel like I understand things so much better now because I learned about these new techniques that people have been using. And I kind of always knew about them because I read about them in papers, but only recently at this conference did I realize, like, all right, I got to start doing this, and called the truncated Wigner method. So I'm using that in numerical simulations now. And Duncan's old graduate student, Wyatt, who we had as a guest on here, we're collaborating with him now because he sent me all this really excellent code that he started using. So I'm even just like 3 weeks ago or 4 weeks ago, I just feel like I understand everything so much better. So it's kind of funny how you're always just learning about things and you kind of change how you think. But
Yeah, and the thing is, I find that understanding or learning this kind of intuition that we get is so non-linear. It's not like I keep learning and my understanding goes up proportional to the time I spend learning. But it's more like we have splash of moments of enlightenment where we have like,
yeah,
oh, I understand this concept a little better. But it's not just like I can't say how better. It's just like I just have this big jump of understanding, and then it's like when we study more, it's more like we are giving us more chances for that to happen.
Michael Berry, he has this I don't want to say analogy, but he says it's his contribution to particle physics. It's he calls them claritons, these sudden moments of clarity. And you can have big ones and small ones, and sometimes you can have anti-claritons where you think you know something and then suddenly you realize like, oh, I completely misunderstood that. And that's I felt like I went to this conference and I got showered with 16 billion claritons. Um, and they all went through me like neutrinos, except one of them actually interacted with me. So I took something home from it. Anyway, I don't want to keep going on about this conference. We didn't have really an intro topic for this because we have other things we want to talk about.
Well, I mean, I think we could go into the process of learning quite a bit because we
Yeah.
have been in graduate school for this is our 6th year, right? And it's quite a long time. And the way I learn or I study and all this stuff is there's so much difference from what I did in undergraduate, and is much less prescriptive. When in undergraduate we have kind of rigid learning outcomes when we take course, right? If we take quantum mechanics, there's like, well, we want to understand the measurement process, or we want to understand the Hilbert space and how to deal with Schrodinger's equations and the new way we deal with linear algebra with bracket notation. And all these stuff are much more prescribed to us. Like, here are these learning outcomes. Go learn it, do assignments. But when now we are doing research and we are basically trying to understand the material by ourselves, I find that I have such a different way to learn things than just like, here, I'll do a bunch of exercise in the book here. Sometimes we go read papers that adjacent to our field. Sometimes we read the textbook, and sometimes we try out the code or look at the figures. And it seems to me, perhaps I haven't figured out after 6 years how to, what is the most optimal path. It's seemingly random, but it's not, right? We probably all have some routine that we do when we were given a subfield. Like, oh, no, go look at this. And then we're like, oh, well, maybe we go on some type of search engine that only look for papers. Or sometimes we look for the papers and look into the reference, what textbook do they cite and all this stuff. So I want to hear from you guys, like, what has been the biggest difference for in terms of self-learning to understand these type of advanced concepts?
So I feel like the way I learn is I kind of just read papers and try and replicate the results. That's kind of what I end up doing, because that's something I don't want to say I can easily do it in my field, but it's something I can do. It's not like, people who build, I don't have to build a whole experiment to replicate someone's results. I can go read theory papers and try and derive the same things they got or stuff
Yeah,
like that. Or
but that's
match.
science, baby, right? Like, is
Yeah.
how to the papers are made to be replicated in a sense, because if it's not replicable, well, what's the point, right? Like, they're just saying something so subjective. That's
Yeah,
well, is there
but
any point of doing that?
a lot of papers are hard to replicate unless you have a lot of, like, you read the paper and you can spend months and months and months reading it, and then finally it clicks and you replicate it and you're like, oh, like, now I could read a similar paper and replicate it in like a day, but sometimes it takes forever to even understand what they're talking about. So I guess for me, the biggest thing, not the biggest thing, but something I've gotten really good at now is just like finding things, finding information. I feel like that was something, like, we did undergrad research at St. FX, but we kind of were just like given papers and given things to do, and like, I don't want to say easy problems, but simpler problems. And now it's like we kind of I don't know, but I come up with a lot of my own problems, and I have to go check, like, did anyone else do this before? Or if I have a question about something, like, I've gotten quite good at just finding papers online and looking into really deep corners of the internet, and seeing and finding information and then reading it and kind of compressing. Like, I'll find a paper, it's 40 pages, and kind of compress down the key message in one paragraph and insert that into my brain fairly quickly. So it's a very good skill to have. I'm still working on it.
Yeah.
I'm not perfect at it, but
Yeah, and I think when you're in a field long enough or have done a lot of research, you can kind of figure out the crux of the paper, or what's important and what's the difference between what you're trying to do and what they did, right? Let's say, like, oh, I'm doing this simulation, I'm fixing these parameters, have these variables, but what they do are the opposite, or maybe they're fixing auto variables and they're changing auto parameters. And then you kind of realize that there's so much similarity sometimes between literature. It's like, well, if we're trying to solve the same problem or provide some type of models to explain the same phenomenon, there's always so many things you can do. And once you learned all learn about all those techniques, it's become much more clear the purpose of your research. Like, well, other people, they're trying to say, for me, let's say the self-assembly or how crystal formation and for colloids. And people try to use, like for me, we use Monte Carlo method to do it. It's Monte Carlo simulation, but you can also do it with molecular dynamics. And people try to put different interactions and different forces to try to explain this. But at some point we are trying to just do the same thing with different techniques, and there are good justification why I do what I do and why they do what they do. And at some point you learn all those nuance, and you're like, well, that's really interesting, because we can only do a few things at a time, right? I can't do all the simulations. So I'm really curious to see what they have and what are they going to find with their methods, because some methods are really difficult to replicate, or one of the main limitation in computational physics is, I think, just computational power. Like my code takes maybe sometimes weeks to run, right? And well, I don't have infinite time where I can test every case or test all the parameters. So at some point, you have to make an educated guess on where am I going to test first, and if the results come out, what is that telling me about where I should test next? What parameters should I change? And I don't know if that is similar to your experience, where maybe in the theory side, or even like for Patrick, when you are doing a field work, you can't just go everywhere, right? You have to pick maybe certain part of the forest, of the jungle to survey, or maybe perhaps you want to do holistically. But like, have we got better at that, right? At being leaving us more probability to find things that work out, rather than when we first start, you try to just find random things and try all these things that you don't really know how it works. But now I think I have a good idea where I should search, where should I focus my effort into in terms of research.
Yeah, I don't know about Patrick, but I've definitely gotten better at that. Pattern recognition. I see something and it looks like something else I know a lot about now, and I kind of make that connection, and I think, okay, if I look at this new system in this specific region, I should see something that looks like what I saw before, because there's some universal similarity between them or something like that.
Well, and I think one thing I want to point out too is that research seems to, at least in science, seem to be like a rational endeavor, right? Like endeavor, like that's like, oh, we try to derive, we try to figure these out step by step. But I find that's not very true. I mean, there's some elements of that, but most of research for me is creative business, which is kind of strange, because you think, oh, well, we physicists, we're gonna sit down in a room like what's behind me in my chalkboard, because to derive bunch of stuff, and we try to figure out the next equation and not. And sometimes you kind of have to do that, but I think most of the time we just stuck in this like limbo of like we don't know where to go next, so we let our creative minds like, oh, maybe perhaps we're gonna do this. So things will figure out if we do this, but I don't really understand or have a rationale why I would do it, but it just seems right, right? And sometimes it just comes to you. It's like this moments of clarity you're talking about. And I find that research is basically a sequence of those moments. So you're like, well, you're gonna do this because I just think it's right.
To me, it's like doing many things, learning how to do things wrong many times, and then eventually figuring out how to do it the right way. So, like, I can work for 3 weeks and maybe not make any progress in my head. Like, I'm like, I didn't do this goal I didn't achieve this goal I wanted to do. But I also kind of learned what not to do to reach that goal. So it feels like you're not making progress, but you definitely are, because you're learning what not to do. That's the way I think about it. At least it makes me feel better about myself.
I mean, I completely agree with that. And I think research and science in general is just kind of learning what not to do more so than learning what to do, because you can read 50 different papers on a subject and then try and be like, okay, what's the best way to apply it? And then you just kind of try a couple things. And I think that's a big thing is whether you're kind of trying to derive something or run an experiment, you're trying different things. Of course, you're taking educated guesses, but there's still trial and error. There's failure and successes. And I would say, at least from personal experience, there's a lot more failures or false starts or kind of going down the wrong path. And it kind of harkens back to a figure that I saw. I'm pretty sure I was in like junior high school when I first saw it, but it was the idealized scientific method where it was like, okay, you have your question, you have your hypothesis, you test it, and then you make your conclusion. And then the actual one was, okay, it's just arrows everywhere. Everything's going which way. You have 3 different hypotheses you're trying to test with the same experiment, but the experiment's failing, and you kind of have some conclusions, but you have to go back. So it's a messy process. And I mean, I think as graduate students, especially, we're more prone to kind of dealing with the failures and learning from them. Whereas, say, someone who's been in the field, like Sir Michael Berry, Sir Dr. Michael Berry.
I guess so.
Yeah. I'm sure that there's a lot more intuition developed. So again, I'm sure there's still failures there. And again, those aren't a bad thing, but I guess you can probably narrow down your educated guesses, which I feel like we've been able to do in the past, well, however many years we've been doing our field. So it's not so much a question of, okay, yeah, we're learning to do the right thing. It goes back to what you were saying, Liam, of, oh yeah, you kind of develop this intuition and you fine tune that intuition over time.
Yeah, I mean, we've only been doing science for what, like 10 years or something? I don't know. You can count high school as well, I guess. But yeah, like freaking Sir Michael Berry's been doing physics before my parents were born. Like, it's hard to compete with that. So you learn a lot, and one day we'll look back at this and be like, yeah, I did okay for not knowing very much at the time.
Well, and also I think it really emphasized the importance of supervision, right? Like if your supervisor kind of keep us in check in terms of, let's say, hey, you're not going all over the place. Here's some direction. Maybe some supervisor are more hands-on, where it's like, okay, this is the path that's well trodden, or this is the path that you're supposed to go. Where some others like, well, here's some general direction, so you can try here, and maybe they give good advice, or they give you, let's say, like here's the methods that people have been doing, and show you the way, basically.
It's kind of like learning how to do a backflip. And I don't know if any of you two can do one. I certainly can't. Maybe a goal, but if you try and learn how to do backflip, you see a video of someone and you're like, yeah, I'm going to do that. Then it might take days or weeks of work to like, okay, how do I do this? And you kind of have this spasm once you're kind of halfway around. Whereas that's kind of the case where you might have, say, an absent supervisor, don't have a supervisor at all. Whereas if you'd say go to a gym and you're like, I want to do backflip, then you can probably learn it in like half an hour at the most, because you have someone to guide you, direct you, and instead of going through that trial and error phase of, okay, what am I doing wrong? What am I doing right? And kind of self-adjusting, you get that external, which is, I guess, expedites the learning process, or whether it's for a backflip or for your subject area. But I feel like they're quite the same. So make sure you find a supervisor who can do a backflip, is what I'm trying to say.
I feel like my supervisor is more likely to do a backflip than I am. Pretty active. But anyway, I have some moving on to some special topics, some special things I prepared for this special 100th episode. I have some questions for you two. So I'm going to do like this little question and answer between the three of us. Oh, my cat's picking the tree back there. I don't know if you could hear that, but I have a little question and answer for everybody. So I don't know how you want to do it. So I'm going to ask you a question, and I can either give you my answer first or let you guys answer, then give you my answer. tell me what you want. Do you want my answer first or my answer last?
We can circle back to you.
Okay. So the first question that I have for you guys is, what is everybody's favorite equation? I'll give you a second to think about
Oh
it.
boy.
There's a lot of equations out there, but just off the top of your head, kind of what is your favorite equation?
Well, I think for me, the easy one is the partition function. And I deal with that all the time. And I
So
think it's what do you call it? It's
what
really
is a
it capture the essence of the description of statistical mechanics to the world, basically.
so you can just quickly summarize what is a partition function.
Well,
That's
actually,
a
I'll put
tough.
it different. I'll put it a different way because I think without showing the math is a little difficult, and maybe there's not that many points to it. But a lot of time you hear this when you learn thermodynamics or statistical mechanics. It's like, oh, if you get the partition function, you know all you need to know about the system. You can calculate all the thermodynamic stuff that you want to know. And you're like, well, it's like if you know the operator and you know the wave function, you know pretty much everything for quantum stuff, right? And why it's so important is that it really shows what statistical mechanics is all about. And to me, it's all about counting. It's like, how do you count? And
1, 2, 3.
right? And what if you have 10 to the 20 to 23 number of particles? Like, how do you count? And you have all these degenerate energy levels, or, if you go into, let's say, Bose gas, like, so how do you count the states? And it's become very interesting because when you do quantum mechanics or you do general relativity, usually you try to limit counting. You want to deal with one particle, you want to deal with one thing, or build a type of field or density matrices or some type of mathematical object to make things be one, right? To one thing. And we do that in statistical mechanics and statistics all the time. But I think one of the things that we address a lot is, well, how do you count the states? How do you count the trajectories of the particles that you're looking at? But when you have a lot of particles, well, how do you count things? And I think the partition function kind of encapsulate that. And if you want to try to make an ensemble, or you try to make to describe a system, and it's nice to have a partition function, which sometimes you really just it's really difficult to obtain.
I really like that answer. Yeah, it's kind of remarkable how you can do statistical mechanics even though there's many, many, many particles. And I guess it's the same with a lot of fields, right? Like you can do fluid mechanics without really thinking about the molecules that make up your fluid. So, Patrick, do you want me to go or do you want to go while you still think about it?
I mean, I kind of have two answers for this. So I don't deal with, I guess, as much theoretical work as the two of you might. I mean, there's still plenty of equations, but they tend to be essentially just summations of one sort or another. The first one that popped to mind is like a little bit of a fun one. Not quite an equation, but it's the sum of all positive integers being equal to negative 1 over 12. And I remember first hearing about this in university when we were first kind of getting started out. And it was like, what? How does that make sense? Just how in the world do you do 1 plus 2 plus 3 plus 4 all the way to infinity, and you get a negative number, first of all, and then you get a fraction, second of all. And there's lots of discussion on it. There's lots of fun takes on it, especially, and I just kind of find it
It's
funny. Like I first heard
the
about it.
Riemann-Zeta function or
Yep.
something, right? I
Yeah,
remember the meme vividly. That's like, oh, how do you solve the trolley problem? Well, instead of run over 10 people, you run over 1, 2, 3, 4, 5 people, and at the end you run over negative 10 1 over 12.
Yeah, I remember that. So,
yeah, no, it's fun because it kind of doesn't make sense, and it's fun to think about. But I do have another one that probably like 5 years ago I would have answered as my favorite equation.
Before you do that, just quickly, like the Riemann zeta function is a really important thing because it's zeros are prime numbers, and people want to solve for what the zeros of the function are because they want to know, are there an infinite amount of prime numbers, or is there a finite amount? And stuff mathematicians are very interested in, and it has like applications in computer science and all these other things because encryption is all about prime numbers and things like that. And the other thing too is that there's all these cool arguments. Like there's many different takes on the Riemann zeta function, and one of them is like an asymptotic one where when you try and count it, the fact that you don't actually go to infinity. Anyway, I don't really understand it well enough to talk about it, but
it's the set of prime numbers a finite set?
I don't remember. But I guess that's the question. But anyway, there's a lot of like infinite series are also a very weird, tricky thing. There's converging series and diverging series, and this is something that Michael Berry's thought a lot about as well. Diverging series, mathematicians used to hate them, but they're really useful in physics, which makes no sense. Like how can you use something that's mathematically like non-converging to describe real-world things that are bounded and should converge? And it turns out that there's like a whole field of math behind it. It's very interesting stuff. But what was your other equation you were interested in potentially? And again, these don't have to be your favorite equations because like that's like a question you might need to think about longer. But it's like just kind of equations you like or your favorite equation that you can think of right now.
I mean, the other one, again, definitely more so like 5, 6, 7, 8, more than I would say 4 years ago, but it's the equation that describes the standard model. It's very long, it's very complex, but it also describes essentially almost everything that we can see and interact with in the universe. Definitely go check it out. Maybe in the video, we'll provide an image of it, and it's something that could be written on the back of an envelope, whether you'd want to or not. Well, have fun with that if you do. But it's the Lagrangian for the standard model, and I mean, it just describes everything, but it does have gaps, and where the standard model doesn't describe everything, and it's because not everything that we've observed, or there are some like fringes of physics that have yet to be explained that aren't described in this equation. But I mean, it does a pretty good job of, explaining everything. And I guess if you truly wanted to, you could go from this equation as like your first principles and work up to whatever you wanted.
Yeah, I'm not a big fan of that equation because I think it's too complicated. But you're right; it does describe pretty much everything on some level. But I've done a few courses on like things and like one on quantum electrodynamics, and you get these Lagrangians that are only like 3 terms long, and already you've got like something crazy complex you've got to deal with. So it's like you see these ones that are the size of a whole paper. It's like, oh my god, there's no way you'd ever realistically use that equation. But you'll use it for very specific problems. You say like, all right, if we're studying like an electron and a positron together, you can ignore 98 out of 100 of the terms, and only 2 of them are important. So it's cool.
Well, to me, that feels more like a library, right? Like if you go to a library, you don't necessarily want to just read all the books at once, but it's a collection of all we know. And I think it's very important to do that. Is that yes, we can combine our knowledge of what we know about all particles that we spent a lot of times and effort in as humanity to describe, and we can just put it in one thing. It's not something that are like mutually exclusive to one another, right? It's something that it's give hope on, some people would say, theory of everything, which we might not ever have, or we might, but I think it's a good effort and it's a good demonstration that no, the mathematics and the theory of physics are consistent, that we can just put it together in one equation.
And you can also do what physicists do, and whatever you're missing, you can just add like a plus C on the end of the Lagrangian and be like, that plus C is just whatever else we don't know yet, and we'll put it in eventually.
My more favorite one is like plus O to the n squared. It's like the high. There's this behavior we know really well, but there's things that we don't understand. There's the higher order terms that we don't know. This O to the maybe n cube or something like that.
So you guys answered yours, so I'll tell you mine now. And mine's kind of like the single particle version of Feely's, although you could have a multiple particle one. But I'm going to say mine's the Schrodinger equation because I think quantum mechanics is kind of neat. So it's this linear partial differential equation. It describes matter via probability distributions and imaginary numbers. So you need the complex plane. It's statistical, like statistical mechanics, although it's different. But like statistical mechanics, it has one single function called the wave function. That if you have the wave function, then you kind of know everything basically. So I kind of like it for that reason. And it's one of these more people figuring out what the Schrodinger equation was and how to use it was one of these huge, significant milestones for understanding of the universe and at microscopic scales, so like matter. And we use it all the time. It has a lot of practical impacts on human life, quantum chemistry, medical science, semiconductors and electronics, quantum computing, and more. So there's all kinds of really like super elegant equations out there.
Yeah, but I
And
think also there is a little what's it called. I know it's debate or problem or issue, but the thing like we like to say if we know the wave function, we know everything about it.
within the
But
theory, within the theory.
yeah, exactly. But the theory, the axiom is that no, wave function describe everything about it, right? So it's
Yeah.
like the little loop. It's like, well, it's like this like cyclic definition. I was like, well, yes, we know everything about it because we define everything to be wave function.
And that's the other reason I like it, is because it kind of adds this extra layer of complexity that like when quantum mechanics was new, people really like even today no one really understands what's going on. They know that probability distributions and wave functions they model the universe really well, but it's like so non-intuitive to our kind of classical understanding of the universe that we still don't fully understand like what even happens when you collapse a wave function, when you make a measurement, when you look at something. So I really like it because it kind of opened up this can of worms. It really furthered understanding, but it also did a lot more.
Right. Because it's explained like I like how Peter Marslin, one of the undergrad
Mm.
profs, put it, right? It's not a theory about nature, it's the theory about what we know about nature. So the measurement process is very important where well we don't really know what's going on when we measure and the wave function collapse, what we know how the measurement process kind of how things evolve if you measure it. Right, it's very important to know that. But the quantum theory doesn't explain when, why, or how the wave function collapse. But we know what it collapses to. Right, we just like if we put this type of operator, or if we measure it this way, the wave function will collapse into into let's say a real eigenvalue or a real number that we can measure. But if we measure it this way, well, nothing would come up because it's going to be a complex number that we cannot measure.
Yeah, it's a weird theory, but it works for sure, and it's very powerful. But moving on, I have two more questions. So the next question is that if you could have any superpower based on a physics/science principle or concept, what would it be? So this one maybe is quite hard to think about on the fly, but I kind of want it to ask it. I'll go first with this one because there's this TV show that I've watched before that I like, and there's this super villain in it. There's like superheroes and super villains, and they have powers, but the powers are kind of science based. Take that however you will, but they like they try and explain it with science, even though you can't really explain superpowers with science because you don't conserve energy, and people are you can't really do it with modern day science, as far as I'm concerned. But there was this guy who his power was that he could change. He had the ability to change the elasticity of objects, so he could basically change the spring constant of anything he wanted, which doesn't sound like that powerful at first, but it was pretty powerful. Like he had to be quite creative to use it in this show. So he he could use it. He could change things into trampolines. He could like jump off buildings and just bounce off the ground. he could make the air elastic. So like, so that it would be fixed at like 2 points, but then bendy in the middle. So he could like just basically walk on air. He could create like little ballistas, like little like bows out of anything he wants. It was really kind of cool that it's not the best power in the world, but like I thought it was like kind of cool that it was like, oh yeah, I can just change the spring constant of things. So I thought
Yeah,
it'd
but
be a fun power to have.
what does that mean, though,
I
right?
know, right? Like,
Right, like spring constant is like a classical description we
yeah,
put into this. Like one thing that I like to put as an example is like if I push onto the table right now, well, it's not exactly like I'm pushing the force. There's force in air quotes, right? But it's just the Pauli exclusion principle that don't allow the electrons to be in the same state,
yeah.
right? So that's really not letting my finger through. But however, there's a very, very, very slight possibility that my finger would go through. So it's like, what does it mean by the changing the spring constant?
Yeah.
But yeah, I know it's a
But
TV
again,
show.
it's like a cartoon, right? So like he could make things elastic basically, in like whatever specific way he wanted up to some limit. So I thought that like it felt like a physics power. It wasn't just like he could teleport. Like teleporting would be one maybe, I guess, but I don't know if you guys can think of one that you might want to have.
I mean, just kind of on that same vein and more so physics related, because the first thing that popped in my mind was the power to refill.
So,
But
what?
that's not the power to refill, which, if you think about it, I mean, it violates the conservation of mass and energy and all that. But bank account's empty, you refill your bank
Oh,
account. Drink's empty, you refill your drink. Someone who don't like splatter is empty, you refill it.
oh my
That
god.
kind of thing. But
Damn.
but kind of more so relating to, I guess, physical properties of things, I'd say the power to change viscosity, which kind of goes with the
Yeah,
spring
that's like a
constant.
different
But
take on it. That's a cool one.
yeah, but like if you could change viscosity of like the air, so as you're falling through it, you just go right through it, but then kind of have this gradient of increasing viscosity for the air, so you gently slow down because your terminal velocity changes, or I don't know. There's a
You
whole
could.
bunch of things.
That's
you could
really
change the
powerful because you
viscosity
could
of.
just change the viscosity of air around a person, and they would just like be unable to breathe or something because it wouldn't be able to go in.
You can just change the blood viscosity and they'll be dead.
Yeah, like that's actually
Yeah.
way better than the elasticity one for sure. Like as far as I'm concerned, I like the elasticity one. It was fun, but that's like straight for the throat kind of superpower. Like you could also it had lots of industrial application. You could go like
Oh yeah,
make a lot of money with it probably.
absolutely. Yeah. No, I think I'll stick with that one. Is changing viscosity.
That's a good one. Bailey, do you have any
Yeah.
takes?
I mean, I got these from all the Japanese animations I watched as when I was younger, and I would say the two. One interesting one that I don't want to have, and the other one that it's gonna be super overpowered. But no, I would do the interesting one. There's this old anime called Darker Than Black, and I don't know if you guys heard of it, but it's kind of people have like superpowers, but you have to pay a price for it and stuff.
Okay.
But like there's this, it's kind of like not science based. It's like science fiction, right?
Yeah.
I think that like the sky was gone because from the war, and then there's like this fake sky, whatever. But there was this girl, Amber. Well, I would say a woman, but what she does is she can reverse time. Well, she would go back. It's like that Christopher Nolan movie, right? You go like you walk forward, but everyone else going backwards, something like that. But every time she uses her power, she gets younger, and it's pretty neat. Right? It is you have the price that corresponds to your power, and so you have like she would like record herself in the cassette, but you have to play it backward to hear what she says and stuff. So it's really interesting show. But the one I want to have is from this show. I don't remember the full name, something with railgun in it. And it was this character called Accelerator. And he's be able to change vectors. Like a bullet's flying to him. He can change the vector of the speed of the bullet, anything with vectors. So he's like very powerful because like no one can like hurt him with physical objects because you throw a car at him, he just changed the vector of the speed of the car to be negative. It just fly back to you. So anything he touch is he can, or like I think touch. I don't remember how he exactly enacts his power, but like you can change the vectors of everything. So that's like you can like accelerate it in however you want.
Yeah, I find like the show I'm talking about was an anime, so like a Japanese show, and I find like these Japanese anime, they actually like think about these powers a bit before they put them in a show. Like a lot of these other, like Superman, I don't think people really thought about any of the science behind it until years later. Or a lot of other superheroes, but a lot of these anime, like they have superheroes and supervillains um who have these really cool powers with a little bit of kind of physics and science thought in there. All right, so my third question now. I have to go find it. Oh, this one. Okay, this is an interesting one. If you could instantly solve one unsolved physics problem, which one would you pick and why? So, I kind of want to go first again. So I was debating between a few different ones when I came up with this question, but I think one question I'm most interested in knowing is what happened before the Big Bang / inflation, and did it even happen? And I think I picked this question just because there's a lot of other problems that I could have solved it, like picked to instantly solve in principle. Like solving the Navier-Stokes equations is something that like people really want to do, but in principle, like I think in principle we could answer that because it's something we can do and test, but we can't go back in time and see what happened before the universe formed. So that I would pick that one because it's not something that like I don't think there's ever a chance of us ever answering. At least we can't really do an experiment or anything to test it. Maybe these analog experiments, but anyway. So I'd solve the question: what happened before the universe formed? Like that's a really interesting question to me. Or you could ask something like, what is dark energy, and instantly solve that. So if you could pick one, what would it be?
What happens inside a black hole?
That
That's my big one. Like,
that was the other
yeah.
one that I was thinking about. In my mind, it's a little unremarkable. There's all these theories about what happens inside a black hole, and it's just like really condensed matter. I mean, that's obviously quite interesting on its own, and maybe something wilder happens. But yeah, so that was definitely one I was considering. And you can do simulations of what it looks like to fall into a black hole. People have done that, but we don't really mathematically there's a singularity at the center of a black hole. And in principle, if we figure out quantum gravity, then we can resolve that singularity and figure out what happens inside. But that's a whole can of worms.
Yeah, and that's the thing. So just currently for fun, I'm reading Brian Cox and Jeff Forshaw's new book titled Black Holes. So that has me thinking about black holes a lot. But yeah, I mean, when we took a general relativity course in our undergrad, it was really interesting to see kind of the different frameworks that you can work in inside a black hole. But there's just so much unknown about them, especially, I mean, my big thing is, okay, you have your event horizon, and mathematically there's a singularity, at least from general relativity. But realistically, is there a surface just like right behind the event horizon, or it? And I know it gets tricky, kind of talking about space and time and everything that happens in a black hole, but oh no, there's just so much unknown about them. And I mean, we have directly observed them now, which is pretty cool, but to actually know what happens, I don't think that's something that would ever be possible to know, but certainly be cool to, I don't know, just poof, we know exactly what happens.
The other thing too is that the universe is more complicated than our models typically. So people do consider more realistic black holes, but we've really dumbed them down mathematically to make them more understandable.
Mhm.
But they're quite like simple objects in some sense. They have angular momentum, they have a charge, they have a mass. I think that's it. And then you could ask all these questions about, all right, where does quantum mechanics come in, and then things get kind of wild. But that's a good question to solve. You would get a lot of citations.
Oh yeah. And I guess that's the thing is like they have very few properties on the outside, but what about the inside? Like I know there's the was it the no hairy balls theorem or the no furry balls theorem? Uh, but in this case, that's on the outside as we
Well, hold on
observe
a
them.
minute. Hold on. The hairy ball theorem, I think, is that if you have a ball and you have like a tangent vector on the outside of it, you can't like smoothly. I can't remember how it works, but there's always like a little tuft that poofs out. It's not like perfectly smooth. And I know that somehow relates to black holes, but I don't really know how. And I just know that people joke about that one a lot.
Okay. So it's the no hair theorem.
Oh, okay.
And what you're talking about is the no fuzzy balls theorem, where if you make tangential
Oh, okay.
point to the surface of a sphere, you will never be able to cover the sphere fully with tangential lines.
Yeah, so
I
the no
believe.
hair theorem is that a black hole has no hair, and that means like they all look the same. That's like, the idea is that if you have like a row of 10 white bald guys, like you're gonna have a hard time telling them apart. So the no hair theorem is that black holes like they only have a mass and angular momentum, and a charge. And other than that, like all the information that went in gets lost, and that's the information paradox. And that's an entire thing we've talked about before, and it's kind of very complicated stuff, which maybe we shouldn't get into.
Yeah. And that's specifically for stationary black holes.
Well, yeah, no,
yeah.
but no, you could have like spinning black holes that have angular momentum, right?
Yes, yeah, but like the no hair theorem states that it's specifically for relates to stationary black
Yeah,
holes.
I think there's like generalizations, the more generic. So you get like Kerr black
Yeah.
holes and Nordstrom black holes and some combination of the
Yeah,
two.
yeah.
But yeah, so like when you do like black holes when they spin, you get like two horizons, an inner and an outer, and an ergo region. And these are things I
Oh
don't
God.
fully understand, but they're important.
Yeah.
All right.
I will just say, sorry, just on the Wikipedia article, the very first thing it says is not to be confused with the hairy ball theorem.
Well, we immediately did that. So anyway, Feely, any problems you would be interested in solving?
Well, not in solving, but if I can slap a finger and solve it,
Yeah,
then
Thanos solving.
yeah. But the thing is, if you asked me that question 6 years ago when I started my graduate career, I probably had a similar um, answer to you, where it's like,
Mhm.
oh, these kind of grand scheme problems that we are just curious about as scientists, as physicists. But now I think have changed as a person. So I would say to the problem of harnessing energy. If we like basically, how do we make the arc reactor that Tony Stark made? Right? It's almost
Mm.
like what? How can we make this like infinite energy basically? And I would like to see what happens to humanity after, because it could go either way. It could go
Yeah.
into like we go into total chaos when everybody's try to harness this infinite energy, and we all ended our civilization, right? Or it could become like a utopia where there's always enough to go around, so that we don't really need to, like this type of basic universal income is like everyone just live the life as they choose, or everybody's gonna not get along. And is I think would tell us not just the science, just like tells us more on like what is the human nature, is human good
That's
or human bad.
that's interesting. What you just described kind of sounds like the plot of the Lorax, like the book and movie, where the rich business guy was selling air, which is like, a free resource as long as you have trees, but people like didn't really, I mean, they knew, but they didn't at the same time. I don't know. It's just like, would humanity live peacefully in harmony, or would a bunch of people exploit the hell out of it?
I mean, that's kind of like Star Trek, where they've kind of figured out those issues of, oh, yeah, we have all the energy we need and we have all the things we need via replicators. So, I mean, I think Star Trek shows kind of the positive side of that kind of future where it's, oh, yeah, we all work together, we explore space, and we try and like expand our knowledge and everything is peaceful. And I'm just trying to think of like some sort of sci fi or piece of media that's the other way of, oh yeah, we have everything we need. And
Well,
maybe the Lorax is one, but that's limited.
I know you heard the show Orville. I think Seth MacFarlane was running it, but I think it's all
Yeah.
like similar to Star Trek. But they also show there was this episode that they show what happened if we, let's say, give the infinite energy to this new this civilization that we found in this on this planet. And it's like, oh yeah, what happened before was that there was just war and they weren't ready for it, right? So there was war and entire civilization, entire planet turned into a wasteland, basically. And these are like thought exercises that come from the scientific discovery, right? I think because I think about science more of the a human endeavor to just not just explain the universe, but I think to improve life, right? And
Mhm.
what happened? I think what your guys' answers were more like, well, this is what we are curious about. It's like this intellectual curiosity. But what I'm trying to think is on the other side, where no, what if we solved the basically sufficiency problem or like this energy problem or things that a branch of science that I don't do and Liam don't do, right? Like we don't do the science that would like change the life of the people or save lives or whatnot. I think I'm just
Yeah.
curious about perhaps there's some application to it, but maybe not to the first degree, right? But like if we can solve the problem of like, oh yeah, we can make materials that withstand or then can clear up cancer or diseases and all these stuff, like is an interesting idea, right? Like if we can solve one side of the coin, which side will you choose? Do you choose to solve the black hole stuff or understand our place in this grand universe, or we try to solve the human problem where it's like, well, how do we, let's say, live forever? Or is that a good thing? Or should
Yeah.
we, yeah.
Well, that's what I was about to say. Is like, you could solve the problem of death and like immortality, and then is that necessarily a good thing, right? What would happen? Who knows? But yeah. So I thought those were just some little. I just wanted to see what your guys' take on those things were, which is it was really interesting to hear everyone's take.
Just to kind of keep on this topic, just a little bit, and science in the news, which I always love to talk about. Just recently, a Canadian firm was able to actually produce fusion, and a successful fusion reaction, I'll say, for a sustained period of time using not a tokamak or like something like the Wendelstein reactor or anything like that, but instead by using a very interesting compression method that essentially did the same thing. So this company is called General Fusion, and they are based in British Columbia in Canada, and they have what's known as like this. What's the exact term? It is magnetized target fusion, where essentially they work with a liquid metal that surrounds a plasma. They can then apply pressure to that liquid metal, which will then compress the plasma. And from that, you get fusion that's happening because the plasma in this case is composed of probably deuterium or tritium or some sort of highly fissile material. But yeah, so this was in the news very recently where their latest prototype was able to fuse. And now they're working on their next prototype, which is called LM26 or Lawson Machine 26. And they aim to achieve fusion conditions of over 100 million degrees Celsius by this year, and then kind of look for actual positive energy fusion by 2026. So it's really cool that we're getting closer to that kind of maybe not infinite energy, but certainly clean and efficient energy that has the only byproduct of, well, helium. And
Something we need more of.
yeah, and it's local, which is super cool too.
Yeah. So I'm wondering. I saw a photo today, just on like I don't know Instagram, Facebook, or whatever the popular TikTok, the popular platforms are now. I won't date myself, but it was like a photo, an old black and white photo of a bunch of scientists pushing a giant, like 1 or 2 person tall box onto a boat, and it was a 5 megabyte storage device, which at the time that was probably revolutionary. They're like, wow, we can store data on this thing the size of a king sized bed, and we're gonna transport it somewhere with this boat. And then now, right, I'm recording this video on my phone, and I'm like, yeah, I got 120 gigabytes of space. Like, I can do this recording from my phone. So I'm wondering if it's like we're 40, 60, even like 80 years from now, will they just have like fusion reactors everywhere and look back at like these people who had these massive experiments are like, yeah, we got net positive for 0.2 milliseconds. And they'll look back and be like, wow, that's so sad.
Well, I remember there's a movie called Ex Machina. I haven't know you guys seen it. It's an
Heard
excellent
of it.
movie about the AI and all that stuff. But there was this quote. Maybe I'll paraphrase. So I don't remember the exact quote, but the billionaire who built robots or whatnot, he was saying, if aliens or people in the future would look back at us and come visit us, like, well, we are like this upright ape with crude tools and navigating this like landscape, right? And the thing about it is, like, we look at cars when they're first conceived, and they were just like bare bones, right? There's no ABS, there's no, braking system. There were all these like really crude, but over not very long time in terms of nature sense, right? Because for evolution to take place and to become really good, it may take hundreds of thousands of years or millions of years. And we develop cars in like 100 years to become, now we have electric vehicle. We have programs in the cars that drive it for us. And if we if we want to, it parallel park for us. Is kind of insane to think about the technological revolution that happened.
hmm It is pretty wild to think about. I wonder what cars will do 40 years from now. They'll make your
Yeah.
breakfast smoothie on your way to work while you're
Oh,
still asleep in them.
yeah. The thing is, like, even nuclear energy was so what's it called? There was so much animosity against nuclear power, right? But if we get fusion power and it has become the norm, things could change drastically within the natural like order of humanity, right? Like, well, maybe when because everyone can get helium and hydrogen. It's like hydrogen is like the most common element in the universe, right? And if you can harness that power, you don't have to mine for uranium. You don't have to, you know, create this radioactive material that have radioactive waste. We have become very good, excellent at managing those waste now. But it would be nice that we don't have to, right? Oh yeah, but the product is just helium that just flies away into the into the celestial bodies or space, or we can just keep it because we kind of want helium for a lot of things. So that would be nice to have that as like the norm. Like everybody, oh yeah, just the fusion reactor down the street, right? Just power up the entire city.
Speaking of another technology that's probably going to be quite different in like the future, artificial intelligence. So I'm doing this clever pivot where I'm going to give you guys some more questions based on AI that I had prepared. Um, so I'm not really going to talk about them in the future, but Feely, you mentioned that I think like the astronomers at your university did this thing where it was like AI science or imagination, something like that, where you showed a photo and people had to guess, was it AI generated, did an artist draw, or was it something from like a science paper or
Well,
something like that?
it was reality simulation or imagination. So it's not really AI, but like yeah, but it could be some AI
Okay.
generated.
All right. Well, I have some version of that prepared for you too. But my version is it AI generated? Is it imagination, like an artist made it? Or is it science? So some data from a paper. So let me share my screen.
All right. And
And just to say, for those of you that are listening and not watching the video, one, go watch the video, but two, we'll post a link somewhere in the description so that you can actually see these photos because describing photos on a podcast is not always the best thing
Yeah,
to do.
I'm not used. This is like our only video episode, so I figured like I got to do something like this. All right, so share my screen. All right, so I've got 8 photos here. Here's the first one. Do you think this is AI generated? Something I cropped out of a paper with data, or is it something an artist made? All right, both of you. I'm trying to think of a way that you can both make up your mind without influencing the other, but I think you guys should just
Yeah,
one of you
let's
should
go
just
for it.
yeah, just go for it.
I think this looks like well, I would say simulation, but it's like if you solve, let's say, a heat equation, for example, right? You get some this
Mhm.
type of heat map, and it looks quite smooth with like may put me on the fence a bit. But if I look at the feature, let's say on the right, it looks somewhat, I don't know, like correct. Like if there's some kind of disturbance there, or like some type of initial condition there. So it's like I would say it's some type of analytical solution to some equation, some which I don't know what.
I would agree with that. It definitely looks like some sort of like numerical solution for something that was cropped out of a paper, probably.
All right, I was gonna tell you the answer now, but I have all the answers written. Actually, I have all the answers written together, so if I go to that page on my screen, you might see all the other ones. So maybe I should just continue through and we guess, and at the
Yeah.
end I'll go through them all. All right, so you guys think this one is data. Number 2,
I'll keep track somewhere.
this image. Is it AI? Okay, maybe yeah. Is it a
It's a little Freudian slip. It's AI.
I'm gonna say
Is
it's AI because I don't think clouds actually have that type of behavior at
Okay,
the
another thing
top.
I so when I say like science is data, it could also just be like a photo of something. So if this was a real cloud, that would be considered like science. An artist didn't make this, or if you think an artist made it, then that's an option.
Yeah, but the interesting part is that yeah, because like if I can have more better resolution, I like to look at noise, right? Because
Yeah.
that's a
Mhm.
thing that comes from photography, and it has this
So
pretty not unique but a recognizable pattern to it. And but you can also simulate that, or you can train probably some models to replicate that. But this
yeah,
could be.
part of this is that like yeah, I just found like I'm not gonna say where I got this photo from, but but the resolutions might not be as good as like I had a photo on my phone and I like emailed it to myself to put on my computer or something like that. So yeah, the resolutions might not be ideal for this, but it's more of like a for fun thing. So
Yeah, if it's real, it could be pretty nice, like what's it called shapes of clouds, right? Like these look so weird. Like I mean, like it could be a trick. Like yeah, there's clouds like this, but I think for this purpose, I would just agree with Patrick. That's like yeah, this is like AI generated.
all right,
Yeah. I will say I've seen similar occurrences in clouds where there's like a wind shear at different level, but I don't think these are big enough for that. So
okay,
yeah,
intro
AI.
image 3.
Oh, they're going to be real.
Is it AI art or well, it's not. Well, I guess it could be a real photo, but I'll give you a hint, and it's not. It's either AI or art.
Or drawing. Um,
I think that's art, and I think I've seen that one before.
Okay, Feely, what do you think?
um, I think also that's art. If it's AI, is
Zoom in a little bit on it for you.
it's pretty good because now that I see the eyes, like the pupil with Patrick, like don't you agree? It looks a little strange, but also maybe the artist is doing that, right? But the light sources into the eyes are a little consistent, maybe because like if it's come from one light source, but if it's not a photograph, maybe the realism is not the determining factor. Uh,
Mhm.
uh,
Yeah, I've definitely seen really good like pencil drawings that are of this quality, or like charcoal
yeah, but
drawings
the
that
pupils are very
yeah.
dilated, right? But they don't hold like a perfect sphere circular form either. So
Hmm.
that this is hard. And look at his suit. Here's the blazer.
Yeah,
The pattern
yeah.
is kind of strange.
I
Actually,
actively picked difficult ones. So
Yeah,
well,
because look
some of them.
can you?
look at the left and right shoulders, right? Are they the same patterns?
Hmm.
Like are they going the same way?
All right,
It almost looks like
all
it,
right.
but actually,
Quickly,
can you zoom into the right side of his face? Our right. Yeah. Oh no, that kind of blurry edge and the
Yeah, I think it's AI. It's very
okay.
good.
I'll go with
Yeah,
AI.
it's
Sure.
very good.
all right. So far everything's been AI. Interesting.
Nope. First one was data.
Oh yeah, sorry.
wasn't it?
Couldn't remember what you guys said. All right. That's 3. Here's 4. So you can probably guess it's not nature or scientific data.
Yeah.
I would agree.
And it's in the iconic 1-to-1 ratio, which AI love.
True. The Instagram ratio.
Dang, can you zoom in on the branch on the bottom?
Like down here.
Yeah,
Yeah.
because what
Okay. The trees have the right shape.
yeah, one thing that I look for is because they reuse a lot of things, right? Like the bush would look like kind of the same-ish.
I
look-
honestly
look-
forget. I honestly forget what this one is. So
Yeah, because look at the tree on the left, right? It's kind of curved. Is that normal?
Yes, that's
Okay.
normal for growing on a mountainside.
I see.
I actually have no.
Yeah,
I don't remember what this one is. So I'm trying to figure it out with you guys.
Yeah, the trees look fine. Like their shape is fine. There's individual branches because I know AI will like sometimes just blur together shapes that look like branches, but when you zoom in, it's not the same.
And also, I'm
thing.
not up to date to like good AI models, so like maybe these are.
Mhm.
Yeah, this is tricky. This is really tricky.
Yeah.
I'm tempted to say this one's like an artist depiction or like an art piece of art. That's not AI, but yeah, the trees look fine, and I think that's
Yeah,
a
it's
good
the
thing.
lighting look fine. Because it's light coming from the right? So
Mhm.
are the shadows casting correctly? Because and also like perspective.
All right. I'll let
We
you
can-
guys pick.
We can. I'll do the art. This one.
Yeah, I will
Alright.
too.
Number 5.
Oh, that's data.
Yeah, I think so too. It's like oh
That looks like it's from a microscope.
All
yeah,
right.
the old microscope data.
Yeah, like polarized microscopy. It almost looks like either that or it's the is it the gram positive thing or whatever it is where like
Not sure
when
what that.
you dye it with iodine.
Oh,
some
I remember
cells
doing
will-
that in like high
Yeah.
school.
Yeah,
Yeah. Or some sick lad just like train AI to draw this. So
Man, spent a lot
Yeah.
of time doing that.
yeah.
All right, so
so
you guys
data.
are 100% convinced it's data. All right. This one.
oh, someone went too hard on the color adjustments. If this is real,
Yeah, it looks like a photograph, right? But are the stars in the correct place? There's so many of them. What's the flashing blue one on the left? Is it a satellite, plane, or?
I don't know
Or-
enough about stars to.
oh, actually, in the top right corner, there almost looks to be like a lens defect. Do you see that?
Yeah,
little,
like the
dot?
blob. Yeah.
Yeah, which I have on my old camera. Like there's something on the sensor.
If you
yeah,
look at
right,
the
on
noise,
the
right? The noise pattern is very consistent, and you
Yeah.
see some a little bit of aberration on the edge of the mountains.
Yes, and this almost looks like someone tried to either stack photos or just used way too high of
or
an
like the
ISO.
HDR. So you combine photo of different
Yes.
dynamic range.
I always forget you two are like professional photographers in your spare time, and you know a lot about this kind of stuff. Because
Yeah,
if you ask me, I wouldn't even think about any of this.
So I think this is a photograph, but it's a combined
I
photograph
would
from
agree.
different exposures.
Yeah, so you think it's a photograph, but it's been like
Yeah.
edited.
Multi-exposure, which you have to do in
Yeah,
this case.
it's
To
like
see that much of the
before the sensors have high dynamic range, the way people do it is basically you take photos of the same thing with different exposure and you combine them. Like because if I'm making everything super bright, the things that have light will be too bright, right? So the things that work in your phone, if you take HDR photos, is the same way to take 3 or 4 or 5 different photos at the same time or like as close as possible, and they combine them to have a high dynamic range photos.
I will say for this one, again, if it is real, if it's not, then well done AI. But in this case, the color editing for the night sky, people need to stop doing it like that. And I think this is just a general complaint is, sure, it looks nice, but the night sky, like when you actually photograph it, whether it's, well, this one's probably
I'm gonna move on. Just for
higher
time's
ISO
sake.
than, anyway.
Yeah.
Anyway, stop putting so much color in the sky. Anyway, sorry.
7.
What could it be?
You tell me.
Can you make this in Microsoft Paint? I think.
Oh yeah, you just make the spray paint like the biggest thing.
Exactly. That's what I was thinking.
But then everything inside of it.
I would say this is data because, like, what would be the prompt to make this from AI? Like, what am I trying to make? Like,
yeah. I would say data too.
Yeah. I don't know what that is.
Something very small.
Yeah.
Yeah, because it's not a star, because they would be more point-like.
I don't know what that is, but I think that's data. All right.
Okay.
Let's go.
And then the final one.
Is it your drawing?
No.
The question mark looks a little strange.
Why are the bounds out? Like, why are there weird things along the top left corner and the top?
Oh,
yeah.
That's me.
Oh, you try to get rid of the copyright.
Yeah, I got the photo from somewhere. Maybe it was from a place that had AI, because a lot of my searching was like AI versus whatever, and I went and read up on it a little bit, and there was some like dates and stuff on this and a name from the photo I got it from, so I kind of splashed it out so it would be as obvious.
This
you
is
couldn't
interesting.
go look it up.
Because it could be like something that is like on paper and was scanned. Because like you see the artifacts around like making things high contrast, right? If you look at the eye or like all the edge of the line of the letters. So when you scan things, when the first image come in, it get processed if it's gonna be a document to have white backgrounds but the thing with that is the things on the edge get blown up like into like high contrast. Into high contrast. And I think that's what's happening here. Or AI just kind of generate this, but I think this is a scanned photograph.
So art, someone drew it, you think?
Yeah, I could be wrong. I'm not 100% sure either.
Yeah, well, these are all kind of tricky. So
yeah, this is tricky.
I kind of want to say it's AI. I'm looking at the shape of the E, and I know AI, again, I don't know what the current models are like, but tends to have difficulty. And these letters look good, but there's also only 2 of them, and the E looks kind of weird. Like, almost like it should be a circle. It looked, I think it could be art, but it also...
And the spiders have incorrect amount of legs.
This is true. It's an insect in this case.
Right? So I don't know
Yeah.
what this supposed to stand for.
Okay. All right. Well, let's go through and see how many you got right and wrong.
Okay.
I'm gonna write
Okay.
down.
So what are we saying? What are we saying for this one?
So I mean, I'm saying art. You can say AI.
Okay.
Okay.
Winners win.
And this will be the deciding factor because we agreed on
All right,
all the other
Liam.
ones.
All right.
Are they all AI?
Yeah. Show us.
All right. So this, actually, I have to open this other thing. Okay. So this was AI, and you guys said it was data. And
Data.
I can tell you what prompt. I just went on like line, found some AI art generator, and I typed in poorly made density plot of Bose-Einstein condensate, and this is what it gave me.
Okay.
Hmm.
So
Okay.
the first one's AI.
Yeah, and second one.
The second one is actually a cloud, like an actual photo of a cloud. That the resolution kind of messed with it a bit because I found it on like Reddit on my phone and sent it over to myself on the computer. But it's a cloud called a lenticular cloud, and they're very weird looking, funny clouds, and it's like an actual, because I follow all these like atmospheric optic subreddits.
It's 0 for 2. Let's go.
Yep. The third one was
How are you sure that the Reddit post wasn't AI?
they're like pretty reputable. They've got lots of nice photos that aren't. I mean, maybe, but like you can go look at the photos people took of these lenticular clouds and see similar things.
So is Morgan Freeman AI or drawing?
No, that was an actual drawing. And it was a YouTube video that's called Portrait Tutorial for Beginners. So I picked something that you can actually go see them draw, just so like there's no debate.
0 for 3. Let's keep going.
This fourth one, I just gave the AI
Bob
Ross painting. So this was AI, and it actually did like I thought it was art, and I'd forgotten.
Yeah, 0 for 4. Let's keep going. Rip the bandage.
This is data, so you got this one right.
Oh, nice.
And it was from a paper titled "Nodal Line Densities of Chaotic Quantum Billiard Models Satisfying Boundary Conditions." Quite the title.
All right.
This galaxy one was AI.
No.
Yeah. I typed in my prompt was galaxy 7 planets light purple. Because I was hoping to get like some planets in there, like and
okay.
Oh.
So I was right to roast the color. Good.
And so so you see these lens artifacts, and it's like, well, the AI does get all of its data from like actual things, right? So maybe that's where it came from.
And we all said all this analysis, and we just wrong, man. Like,
can you zoom into the rocks just quickly?
I zoomed in on them at one point.
Yeah, I
tried to give you a hint in there.
Wow.
But so like, again, I don't know where the AI models, like how they make these. So I know they take real photos and like
they're trained on real photographs, right?
So it's tough.
Yeah, but it's like the thing with the on the left, which is the little blue thing, is like, what could it be, right? Like, and I think the fake artifacts really just got us.
Yeah, no, it's not easy. Like I know because I did it, but I don't think I got any of them right either. 7. This was, I think it's AI.
What do you think it's AI? Is it or is it not?
I have to read the description. No, that's a paper. You guys are right. Sorry.
Okay.
Heck yeah.
Okay.
Yeah, so it was a paper called "Making the Unmodulated Pyramid Wavefront Sensor Smart 2: First on-sky demonstration of extreme adaptive optics with deep learning." I don't really remember at all what the photo is of, but this is something that like I believe, like if I saw this, I could say it's AI. Like, I think that's AI maybe, but you guys were right for this one.
Yeah, because like what kind of prompt are gonna be?
Well, like some of the prompts I've given these things spit out crazy stuff.
Okay, so
and then this was art. So this is actually
all right.
something. So I accidentally gave it away with these little splotches because there's like names and stuff there, and I was like, ah, shit, I forgot
But
about
it could be
that.
the AI sometimes put like copy marks in there, right? Copyright marks.
So that photo was from a Michael Berry set of notes called "Some Quantum Classical Asymptotics," and that's actually like a drawing of him or something someone made. Like
Oh,
again, I have no clue who came up with this or what motivated them to draw it this way, but it's in his notes and they're like some paper in the 80s or 90s or early 2000s or something. So that's like you're right, Feely. I'm pretty sure it was scanned. Um,
Yeah.
and there was more
Well,
artifacts in the E that gave it away too much, so I splotched them out. So I kind of cheated a little bit, made it harder for you guys, but
nice. Well,
yeah.
I mean, if this is an
yeah,
exam, we failed.
But it's really
but
interesting.
you won, Feely.
Yeah, so Feely, congratulations.
Thank you.
I don't have
Winners win, you know?
winners win. Uh, um, but yeah, it goes to show that it's like, when AI became a thing, the first thing like I thought of, maybe not the first, but one of the first things I realized is like no one's gonna know what's true and not anymore. And even if you're like fairly confident, you don't know for certain anymore because it used to be that like if you see a video, it's like that's the proof, or a photo. You're like, oh, how do you know this is real? It's like, well, here's a photo or a video of it happening. But now we can't do that. You
Yeah,
need to
it's
like
kind of easy to fake.
you need photos from people who have shown to be trustworthy in the past, kind of thing. You
Yeah.
need like built up trust. You can't just show up and present something without people knowing who you are, or else people will question it, and then you kind of have to, or you have to prove in some way that it is real. So
Yeah,
I
and
thought,
these things got so good that like sometimes like things are so consistent that I thought it was maybe sometimes human are less consistent actually. They will like make mistakes here and there.
mhm,
But oh man, I'm disappointed in myself for the AI one of the galaxy. Like perhaps if I
Yeah.
were better
Agreed.
at astronomy, I would notice like, oh yeah, the Milky Way it doesn't orient that way, and there's all the stars that are missing or things that shouldn't exist. So I blame myself in the lack of knowledge of astronomy.
well, honestly, like, yeah, I wouldn't have no clue about any of those because it's like if you don't know, then you second guess yourself so many times because of the how good AI's gotten.
Yeah, for sure. It's crazy.
So where are we at right now? So we're getting close to the time, and I kind of have one more quick thing I wanted to mention because we've been doing this podcast for quite a while now, and I'm pretty proud of it actually. Kind of how committed we were to this, how we managed to stick through it for 100 episodes, which is I didn't actually think, I thought it might fizzle out after 10, but we somehow made it through all the scheduling conflicts and committed and came out with enough topics to talk about for so long. Um, so I just wanted to point out that we have an overleaf document that we use to organize this. Um, so we write all of our topics in there, and we kind of keep track of what we've done, and it's currently 330 pages long. Includes everything we've done on the podcast, pretty much. So we've got, I'm so proud of it. I kind of like, if it wasn't so chaotic and messy, I'd like put it on the archive or something. Like it feels like I'm so proud of this document that we've created.
We gotta print it out and buy it. Get like some nice hardcover, and it's
Even
like
though,
Yeah. If you'd like to
you know
sponsor us and keep us
you
going,
know
you
how
can.
some professors have their like thesis like in like books in their office, right? And I was like,
yeah,
hey, what is this? This is the maybe we'll go through and edit it at some point, just like to make it nice and everything. But we will see what happens.
yeah. So it's pretty big, and there's like millions of typos and incomplete sentences and stuff in it because it's just like rough notes that we use to kind of like plan and organize episodes and keep track of what things we might want to talk about in the future and what guests we had and things like that. So that's cool. And the other thing is that I went and it took me a long time, but I went through kind of like all the episodes and I counted who did what. So how many times did I talk about an intro topic, or did Feely talk about an intro topic? It took me like an hour and a half to do it, like
Oh
2
my
hours,
gosh.
because some of the in the overleaf document, sometimes we wrote it down, sometimes we didn't. So then I'd have to go listen to the episodes and like pick through points and figure out like who's doing what. So there might be a little bit of error. I think I've got the numbers right, plus or minus 5, maybe. But yeah, so I went and kind of collected the stats of who did what over the last 3-ish years. So intro topics, main topics, and stories that we were each in charge of. And, we all contributed to everything, but like who was in charge of presenting what, as well as how many guests we each contributed. Yes.
I will say, before delving into this, Feely edited.
Yeah. So
every
I'm
single
about to make a
episode,
point of that. Like,
which is
it doesn't matter how many topics we did because we each pulled our own weight in this, and Feely probably pulled more weight because he edited everything, and especially this 100th episode is going to be a lot of editing for him. So I'm not, this isn't to like throw shade at each other and be like, oh, I did more than you, because in reality we all did the same, roughly, I'd say, and maybe Feely did more than us, Patrick.
No, we all have different what's it called, like environments and things to have to deal with in our personal lives, right? Sometimes it's like, let things happen, and to keep it together. It's not like, hey, I'm gonna make you do more work because we have to be equal. We just play it by ears, at the end of the day, it's just friends hanging out, making a podcast, and it's much simpler to do, right, these days than if we were to do this 15 years ago. It's a lot of effort.
Now there's a lot of software after COVID, right? There's like all this great software, and even Zoom and Discord are very useful. So it doesn't matter. These stats don't matter. I was just kind of interested in them. So episodes, I just want to like point out episodes where we had guests and we didn't really have a main topic because the guest was the main topic. I just didn't count that for anyone. Or episodes where multiple people contributed. So there's a few like main topics where we just kind of winged it, the three of us, and I just counted that as like the three of us.
We never winged it. What are you talking about?
No, we did on purpose though, like a few times. We're like, this is a more chill episode. We're just gonna talk about whatever. Or there's an episode you weren't there, and me and Feely just went on about like math for an hour or something silly. Or there's times where I had an intro topic and Feely had an intro topic, or you and Feely did, or whatever, right? So I would count like both of you. So I kind of I had a metric. So yeah, let me open that here. I won't share. I'll just tell you because it's just like paper. I just had like some written down notes on paper. So for the intro topics, Patrick had 41. So Patrick did 41 intro top, and you're gonna notice that this adds up to way more than 100 for some of them. And that's because, again, like a lot of us contributed multiple per episode. So, or if there wasn't an intro topic, for example, I just count all three of us, or I don't count us at all. I don't quite remember what I did, but anyway, it's all relative. So Patrick, you did 41 intro topics. Good job. Sorry, I lost my photo here. I did 53 and Feely did 28. So that's the intros. The main topics, Patrick did 29, I did 32, and Feely did 23. And then for the stories, Patrick was the real MVP there. Patrick did 51 stories, or is it 57? 52. 52 stories. I did 23, and Feely did 26. So in total, Patrick led 122 things. I led 108, and Feely led 77. And again,
good number.
So we all did tons of work. Like Feely had to edit everything and deal with my coughing every time. Because I cough a lot, it turns out. So that's what we contributed for the intros, mains, and stories. And of course, the how to reach us, Patrick just won that one. I think, me and Feely never did a how to reach us.
Yeah, even when I wasn't here, I still tried to do them.
And out of 99 episodes, or I guess 100 now, including this one, we had 31 guests. So that's 30. About a third of our episodes were with guests, which I think is like a fairly good ratio. Maybe a little higher would have been nice, but that's a respectable ratio. Patrick, you contributed 2 guests, so not too many, but I'm gonna grill you for that one a little bit.
Fair enough.
Nah, no, I'm just messing with you. You contributed 2 guests, I contributed 16, and Feely contributed 13. And I think it's hard because you don't like you're in a new field now where you're working with people who aren't physicists, and to come onto a physics podcast is a little intimidating. Like I talked to some of our guests who aren't physicists, and they're like, "Man, I thought this was going to be like a brutal experience. You guys are just going to be throwing equations at me the whole time." But they all had really good times, as far as I'm aware.
Yeah, this the fear of physicists, like, oh no, we just think we are right.
I don't think I know. No, anyway, so yeah, I was just interested in those stats, and I know Feely. I don't know if you can tell us some more stats about the podcast, because I just wanted like 100 episodes. I'm pretty proud of us for doing it, and we're not like world famous podcast, but if you've got any interesting stats, um, oh wait, Patrick, did you bring Grace on? I thought Feely did.
I thought I brought Grace. I'm pretty sure I
Okay.
messaged Grace.
We brought guest Grace on.
Yeah, we brought
Okay,
Grace
so
on. Yeah.
Patrick, you get 3 instead of 2. I just assumed Feely
Yeah.
did that, so that's on me. Again, there's some error in these, like plus or minus a few, maybe. Especially for the intros, main topics, and stories, because I went through them like late at night, and I was getting tired, and I some of them weren't written down, and I had to go into the episode and listen to it, and I just noticed that like in the intro, Patrick was doing 80% of the talking, so I just kind of counted that as a Patrick intro sometimes. For example, or Feely or me or whatever, right? So I could be slightly wrong, but I didn't feel like spending more than 2 hours counting this, so here we are. So that's kind of interesting. Feely, do you have any interesting stats about the podcast you want to share?
Well, there's some analytics that I'm looking at, and apparently for 99 episodes, in terms of gender, we have 70% male, 28% female, and 1% like authors, like non-specified and such. Most of the age range for our podcast is actually the biggest one is 23 to 27 at 54%. And then
Wow.
we have 28 to 34 at 17, 45 to 59 at 15%, probably our parents.
I thought the parent age range would be the most viewed because of like our
So-
parents.
We have actually from geographic locations, quite a few. We have mostly from Canada, comes in at 58.5%. And the second is United States, 29.6. And then drops down a lot to like United Kingdom to 1.8. And there's Germany, Australia, Thailand, Ukraine, Austria. In terms of platform wise, most of it is from Spotify at around 37%, and then Apple Podcasts at 28%. It's quite interesting to see.
In addition to that, I have some YouTube stats because we do post on YouTube. This video will be going up on
Are
YouTube.
we caught up on that?
And
Nope. I will
we're-
try to catch up before
let's-
this episode release.
Okay, you're busy. Your union's on strike and everything, so I don't.
Yep.
But we do have the latest episode is the hidden nature of electric fields and the Aronov Bohm effect. That's our latest one
That's
published.
probably my least proud episode. That was a rough one for me.
Oh, boy.
But it is what it is.
But in terms of views on our YouTube page, we have 2.4 thousand views. We have 150.8 watch hours and 42 subscribers. Our most viewed video with 141 views is How Literal Nothingness Will Destroy the Universe, which is
False
episode
vacuum,
59.
false vacuum decay, which was a hot topic
Yeah.
at my analog gravity conference because people want to create that in analog system.
Let's see, is there anything for the audience? Oh, that's taken a while to load. But yeah, make sure to subscribe. No, let's see, geography. Most of our views have come from the United States, so about 21% of our views, followed by 2% from Canada. And then it goes Germany, France, the UK, Spain, Australia, and it just shows those top ones. Much of our traffic sources are just coming from people browsing on YouTube, so that's pretty interesting. that people are just coming across our videos. The only two demographics that we have enough data for age are 18 to 24 years old and 25 to 34 years old. So no one outside that age range has watched our videos enough to actually quantify the data. And then it's 18% female, 82%, 82% male, 18% female. So kind of matches what our other stats are showing too.
Consistency.
There's a pie. Yeah, exactly. So lots of, and it actually has it based on seasons. So based on playlists.
Playlists are
However,
seasons.
our most, yes. So our most viewed season is season 6 with 563 views, which makes up about a quarter of all views. So whatever we did in season 6 was apparently really good.
Well, yeah. If my season 7 is not really updating to, I think in season 6 I was really consistently uploading on a good schedule. But I think season 7 rolled by. It's like last year or PhDs, hopefully, right? So everything was chaotic.
Wait, what season are we on now?
7.
Oh, okay. So, geez, I lost track. All right. Yeah, this season's been a little non-consistent, but it's fine. We're still doing it. Yeah, I really liked a lot of the episodes in season 6. Now that I'm just looking at the list of them right here, as well. Like we had Austin Farrell talk about optics and stuff. That was really cool. So many cool episodes and guests we could talk about. Like we already have, I guess. So we can listen. You can go listen to those if you want to.
Yeah.
But anyway, that's everything I prepared. I just was interested in. We've talked about the history of this podcast a bit before. I don't know if you want to mention anything, or you guys have anything you want to say.
Well, I will say, since we've talked about stats and the YouTube and everything, is that although this may be kind of not necessarily an end for the hyperthesis, it will be more so of a we'll get to it when we get to it type of situation, at least for the foreseeable future. You can still reach out to us. You can contact us over email, you can which is hyperthesispodcast@gmail.com. You can send us questions if you have suggestions for future episodes that you want to hear, even if they are fewer and further between. You can send us an email to make recommendations or suggestions. We'll still be interested in taking guests and maybe arranging with them. So chances are, if you are an expert in your field and you'd like to come chat with us, we'll be more than happy to schedule a time. And that might be really the motivation that gets us to get some episodes out. If you are a bit more modern and don't want to use email, you can find us on Instagram. We are at the Hyperthesis. You can follow us for updates. You'll see some pictures related to this episode, and you'll find out when we do make new posts. You can, of course, also send us a DM on Instagram, and we'll be sure to still check our social media accounts from time to time, just to make sure that we aren't missing very important messages. If you're listening to us, you have found us. Again, this is kind of the end of your regularly scheduled programming, we'll say, and also episode 100. So if you are just listening to this episode as your first episode of the Hyperthesis, you have 99 others to go listen to. So go listen to them, share them with your friends, with your family, with your enemies, with whoever you want. Play on a PA system in a grocery store. That'd actually be pretty funny if someone did that. But we are found and based out of Spotify, but we can be found on whatever podcasting service you use, whether it's YouTube Music, Apple Podcast, Audible, whatever you use, we're there. And still feel free to give us a rating. I'll tell you what, if we get 1,000 5-star ratings, we will start back up on a regular season.
Oh,
so
no.
Share us if you want to hear us.
You didn't ask us first.
No. If we get 1,000 5-star ratings, we will come back.
All right.
So share
I'll
us
do it.
and get in touch with us if you have questions or comments.
All right. Any closing note, Liam?
Yeah, it was an honor just a fun little project. And I know, like you said, we're gonna come back, and we're gonna probably we're just gonna come back and make video. We're not gonna make videos consistently. Maybe, I don't know, every few months or something, we'll get together and make a video just to like catch up and stuff and talk about some new topics in science. Or maybe we'll get a guest that's really interesting to talk to, but it's not gonna be like we've done in the past. So yeah, it's not the end, but it's kind of like I don't know what to call it. But yeah, I've had a great time doing this, and anyone who's listened, I'm very thankful to you for listening. So, cheers.
Yeah, it's a natural transition into, or like progression of evolution of our podcast into something
Yeah,
that's maybe more occasional, right? It's like something that prompts it. Now that we know that we can do this media, and I think, have grown a lot as a person, as a communicator. I remember the first couple of few episodes, you were like, there are things like how to speak well, maybe a lot of ums and and a lot, maybe struggle to find words, which we still do, right? Sometimes we don't know.
I definitely still do.
Yeah, how to be concise, or how to choose the proper choice of words.
How to describe things without, a blackboard in front of you is also. I remember the first few episodes, I really struggled with that. I had to think before I talked about, like, how do I describe this when we do our recording later today. And now I just kind of do it on. I don't want to say do it on the fly, but like, I'm definitely much better at trying to make analogies and make things easier to picture if you don't have like an actual picture in front of you. At least I think I am. I guess, the audience could tell me if I'm wrong. They're just confused all the time when I talk, but I hope not.
No, I think it certainly helped with science communication and kind of improving ourselves and how we can communicate in a different way. Because, I mean, during our undergraduate, everything was conveyed over a blackboard. And I was actually reminiscing about pretty much it was only a blackboard or a whiteboard and not really slides or anything. And to be able to transfer that knowledge from visual to audio is really quite a good skill to have, and something that not a lot of people can do. So I think this has helped all of us grow in that sense.
Yeah, I think my final note, not really a take home message, but, things to think before we get to Patrick's story, is this. I think as men, we don't say this enough. So I say, I appreciate you guys, and this has been an incredible journey, and I love you guys. This is amazing. It's just been, and we don't say it enough, honestly, right? Like in between the camaraderie between men, we just, we don't say it, but I just want to say it publicly, right? This is great. It's been like a little refuge sometimes. We are struggling with our things in life, but there's something that's somewhat constant that we go back to, and we enjoy ourselves. So I really appreciate it.
Yeah, anyone who's listening doesn't hear it, but after we finish our recording, then we start complaining about our actual life. We're like, my job, like I got to do this, and it's annoying, and so we kind of like get vent to each other in between recordings, or before and after we record. And it's one of the other purposes of this was to like just this podcast forces us to do things and read things that aren't our main research topic. It's very easy to get tunnel vision, because we do research. The whole point is the tunnel vision and learn about something very specifically. But keep your horizons broad. And yeah, love you guys, brothers. But this was a very fun experience. I had a great time.
Yeah, it's been great. And I know we started this kind of not quite the tail end of the pandemic, but when we were still kind of stuck at home and couldn't really do much. And it was a weird transition going from seeing both of you every single day, weekends inclusive, for 3-ish years straight, to not seeing any of you. So it's been great to hang out with friends, and it's been great to just chat and kind of go back to when we were all together in person and just sit there for hours just talking and maybe avoiding work to do. And I feel like this was a really nice extension of it. And I can't think of two people who I would prefer to do this with besides you two. So I love you both too. And this has been an excellent journey. And the fact that we are still talking 6 years after we really, last hung out and were together in person, aside from
little mini stint.
the occasional time. It's really quite nice.
Yeah, our old prof, Peter Marsland, we have this like big Discord that a lot of us still talk in, and that's how we even organize these recordings. And he mentioned that he's never really seen anything like this, where a group of people graduate together from not his physics department, from the St. FX physics department, kept in touch like this, or even like me and Feely and Dean wrote a paper together. It's like and I'm collaborating with Wyatt, who's another physics graduate from St. FX. So it's like we've got something special for sure. I'm sure other groups of people do this kind of stuff too, other departments and physics departments, but quite happy we managed to pull it off as well.
Absolutely. Yeah. We had a special group and we're all still in contact, and yeah, it's nice that things like this happen.
All right. So with that, I'll let Patrick tell you one of the last story for a while.
Yes. So when I was trying to figure out a topic for a story, considering I've done, 52 of them?
I think I've done 20, you've done more than double what I have.
Wow. We've covered a lot of range of different stories, from historical figures to some fun historical stories of how things came to be. And I figured today I kind of go on that history kick again, but I wanted to relate it to something that had to do with 100. Because 100's it's kind of this arbitrary number for whatever purpose, but it's also special because of the fact that we count in a base 10 system. For a base 2 system, for example, 100's not very special at all, or really anything outside of base 10, maybe base 5, but that's questionable. So trying to think of, okay, what is significant about 100 and what uses 100 that's so significant? And in thinking about that, my mind started turning to how we can measure things, because that's what I like to do, is just measure a whole bunch of things. And the best way that we can measure things is in a way that helps us all be on the same page. So that when I'm talking to Feely when he's overseas, or talking to Liam, who may also be overseas, we can all kind of communicate in the same way. And now we all speak English, of course, so that's easy. But let's say I want to know what the temperature is. What's the temperature in Hamilton or Kingston right now?
I'd have using my phone to record. I can't check.
Well, it's 9 degrees 9 centigrade here.
There you are. And so for much of the world, we use the metric system. And so to celebrate 100, I figured I'd do a little brief history of the metric system. There are certainly other systems in use, both historically and in the modern day, some of which are archaic and should not be used anymore.
Or some the freedom unit,
Like I said, archaic and shouldn't be used anymore.
13 fighter jets per hamburger.
It's like, how long is this? It's about 3 football fields.
Exactly.
Banana for scale.
And these arbitrary units have been used throughout history, like the furlong, the league. There's
I think they make sense within some context, but they're not easily, translatable.
Exactly. And that's the thing is, even if you look at football fields between the US and Canada are different sizes, because there is Canadian Football League and then the National Football League, which is the American one. So there's an infinite number of ways in which you can count things. And so as a way to standardize that, we now, for most of the world, are on the metric system. But if you look at the beginning, the metric system itself is also arbitrary. So let's delve into it just a little bit. I'll try and be a little bit quick with the story, but let's talk about the metric system and where it came from. So the metric system itself began during the Age of Enlightenment, which was driven by this kind of increase in the want to understand the natural world. So around this time, there was a lot of different famous kind of scientists, as we would call them today, but they may have been philosophers or artists or other types of people. And the conclusion was that, we need a decent way in which we can express what we're measuring, what we're observing about the world. And so even in times as early as the 9th century, and of course before, we have measurements from ancient Egypt. That's where the digit comes from. But even in the 9th century with Charlemagne, who was a Roman emperor, he attempted to standardize units within his empire, which later diverged because, of course, the Roman Empire did not last forever. But the idea of having some sort of standard measurement, it has existed for millennia. I mean, even in England, the Magna Carta, which was created in the 1200s, also stipulated standard measurements. And I think there's an excellent XKCD comic on this where they talk, there's 3 or 4 different types of USB-Cs. We need to standardize this and make just one type. And then now there's 5 different types of USB-Cs. So in this case, by creating a standardized unit, you're just adding one more to the mix. And now there's, instead of 12 standardized units, there's 13. Now, of course, we have evolved a lot since then. And that includes, for example, adding 0 to our numbers and moving away from, say, Roman numerals to something that makes a bit more sense. So this includes the introduction of the Hindu numerical system, which was crucial for the development of the decimal system. And then, of course, there's also the use of Arabic numerals, which, again, are kind of based off of Hindu numerals. So there's a lot of different ways in which we could represent these measures. But then it came to actually understanding, what's the standard for these measures? So early standards of length, for example, often relied on body measurements and other types of artifacts. So, for example, we still have the foot, we have the yard, we have the inch. So all of these different things are dependent on people. For example, I forget the direct conversion because it's not used anymore, but there's a certain number of steps, say in a furlong, a certain number of furlongs in a mile, and just on and on. And again, we don't really know as much about these because they aren't as used anymore. However, the problem with using people's bodies or artifacts is that they are either irreproducible. So, I mean, people die, and so you can't just go back in 100 years and try and measure a king's foot because it wouldn't be there anymore. Or objects get stolen, they get worn, they get lost. So there's a lot of invariance. Now, one of the first ideas of an actual standard of measurement that would be reliable across the world came from the invention of the pendulum clock by Christian Huygens. I know I'm pronouncing that wrong again, but in 1656, this pendulum clock was invented, and the idea that, based on the length of the pendulum, we can use that as a standard unit. But this was not quite as effective just because gravity does change in places. So there would be slight differences in the length of the pendulum depending on where on the Earth you were. Now, it took until the late 1600s until Gabriel Mouton proposed a decimal system of length that was based on the Earth's dimension. And now this required the understanding of the shape and size of the Earth. We've talked about this a few times, but essentially in this case, they said, the Earth is close enough to a sphere. So what happens if we measure the length from the equator to the North Pole and use that as a standard? So again, this is kind of where it's arbitrary because it's based on the Earth. And again, all life that we know about that's intelligent and is able to measure is from the Earth. So until we find something else, then It's the best that we've got. But essentially, by looking at the distance, or a quarter of the distance of the Earth, or the circumference of the Earth, we'll say, and then dividing that by 40,000, you could then get what's known as a meter. And so this required very accurate calculations of the Earth itself and trying to figure out, okay, what is its shape? Is it spherical? Of course, Isaac Newton said that the equation or the equator would be bulging. And so there is this idea that, okay, 1/40,000th of the of this distance could be a standard because the Earth isn't changing its shape anytime soon. And this problem became more and more important to solve because by the mid-18th century, there was a lot more communication between different nations. There was a lot more trade. We started to have steam power and steamships and all of this. So it was important that people were able to make the same measurements. So when you're trading, say, wool between France and England, that they're measuring weights the same. Now, James Watt, who is, of course, known for his unit, the watt, advocate for a global decimal system, which linked the length and mass via density of water. Because water is so present, everyone has access to water. So we would be able to use that as a standard. And a French proposal in 1790 to base 1 meter on the period of 1 second pendulum failed because of disagreements. But the first practical realization also came during the French Revolution in 1799, where they were able to have this measurement of the Earth's circumference and then taking a fraction of that to be the meter. And so this, around this time, there was this French Académie des Sciences, which appointed a panel that was able to recommend this decimal system with the unit length, the meter or mètre, based on a fraction of the Earth's meridian. And then they also invented kind of a standardized unit for the weight, known as the kilogram, which is based on a cubic decimeter of water. And these were accepted in France in 1791. And so, sorry, I did misspeak a little bit earlier, but the meter was defined as 1/10,000,000th of the distance from the North Pole to the equator with a meridian running through Paris. So it's 1/1,000,000th of a length. And again, the length is arbitrary, but it was what we used as a meter. And then from the meter, we were able to get the kilogram because once we had standardized meter, we knew what a decimeter is, or 10 centimeters. And then we can measure the amount of water that is within that 1 decimeter cube space, otherwise known as a liter. So we now have length, we have volume, we have mass. Now, for the kilogram, it was you couldn't just kind of weigh out water every time because you needed a standard size of a volume, a standard temperature of water. So what was known as a provisional kilogram, also known as a grav, was created to essentially be the kilogram. And so this was a metallic standard that was made that was the reference for the kilogram. So for the longest time, this object, which kind of was shunned beforehand of, oh, we shouldn't have objects for measure, it now became the measure for a kilogram. So funny how things kind of come back like that. Now, in this case, it was, of course, a lot more valuable and a lot more consistent. So it was made out of platinum, which wouldn't tarnish or change form or anything. And so the kilogram became defined as whatever the weight of an object is. Again, based off of some interesting and kind of sound principles. But of course, objects will lose mass or they might even gain mass. They'll change shape and form over time. So there was this kind of early metric system. Now, old measures still did persist, of course, and when Napoleon went on his conquest of Europe, he implemented a hybrid system, which included the metric system. And then at the start of the 19th century, so kind of after the time of Napoleon, the French Academy of Sciences, length and mass were formally defined based on these objects. Now, in 1832, Carl Friedrich Gauss made the first absolute measurements of the Earth's magnetic field using a decimal system based on the millimeter, milligram, and the astronomical second, establishing time as a necessary dimension. And so time is something that's kind of universal, where 1 second is 1 second, and that's something we agree on, thankfully. I can't imagine if the Americans used a different type of second, the freedom second, if you will, or the New York minute. Anyway, so there was a lot of work towards the standardization of the metric system in the 1800s. People who worked on this include James Prescott Joule, who demonstrate a relationship between mechanical work and heat, leading to energy as another unifying concept and unit. Because we were starting to really get steam power, we want to understand how energy and have a standard unit for that as well. So there was really quite a lot of work, which I wouldn't delve too much into. But essentially, things went into, a lot of work went into creating standards for methods of measurement that derived from length and mass and time. Now, of course, nowadays, we have a few different definitions. So up until recently, we still had quite a few standards that were just kind of outlined as an object, especially the kilogram. There's an excellent Veritasium video on that where he has the smoothest, roundest object in the world, which is quite cool. But now we've switched to how we define things. So, for example, the meter is no longer defined off of the meridian running through Paris from the North Pole to the equator. Instead, it's defined off the speed of light, which, so far as we know, is constant in a vacuum. Again, so far as we know. If you're listening to this in like 100 years and we've discovered something different, check that we're live. Anyway, so now a meter is based off of just 1 out of 299,792,458. And so that's the definition of a meter tied to this universal constant. Similar with time, it's now based off of the amount of oscillations cesium atoms make per. And so a second is defined, again, on this kind of universal quantity where whether you're here or you're in a galaxy far, far away, you would measure these oscillations of cesium the same. And now the kilogram has also been redefined, and it's actually based off of quite a few variables, including the Planck's constant. And so we had to measure that very accurately. And so now these all are grouped into what we generally call the metric system. But what is more, I guess, legally known as the System International, or SI units. And so it's quite a lot of units. And now, just as a very brief overview, we have the kilogram, the ampere, the Kelvin, the mole. And again, Kelvin is based off of the centigrade anyway. And we no longer need physical artifacts to measure these. And this is, I guess, getting technical at this point of, okay, how much do we agree? How much uncertainty is there? But by having these standards, we can kind of go forth and use them and we can agree. So much like how English is the language of science and mathematics is the language of physics, we have this other universal language of units and how we can measure things. And so I can say to someone across the world, hey, it's 26 degrees, it's minus 40 here, and they'll understand, oh, that's cold. And so I think in terms of science communication and communicating science, having this SI unit is incredibly important and it brings the world a bit closer together.
Thank you, Patrick, for the story. Well, since it's going to be end of era, I'll end this episode off with a poem from my favorite poet, William Blake, who's kind of anti-science-ish, but it is what it is. So it goes, the first 4 lines is, to see a world in a grain of sand and a heaven in a wildflower. Hold infinity in the palm of your hand and eternity in an hour. thank you, everybody, and take care.
Bye, everyone.
Thanks for listening, and have a good one.